Okay, so thanks a lot for coming. My name is Šimon Tóth. I have more than 20 years experience in the industry, roughly 15 years of that with C++ as my primary language. But these days I just write and talk about C++, which is why I'm here talking about ranges. The slides are already online, you can grab them. One thing about the slides are just a series of examples that I will guide you through. And because of that, I actually took the effort to cross-link all the examples to Compiler Explorer. So if you want, you can then go there and play with the code. So I will leave it up for a little bit more so people can take screenshots and whatnot. Everyone good? Okay. Now, this is the most important part. Ask questions. And I really try to make this talk approachable, but I'm still talking about generic programming. So this will be quite dense when it comes to information. So if at any point you feel lost, you don't understand something, perhaps you see some syntax that you are not familiar with, feel free. You don't have to raise your hand, just shout out the question. It's totally fine. And I also need to promote my stuff because, as I said, I just write and talk about C++. So I have out one book that's about the standard algorithms. It's content complete for C++20. And the best thing for you, it's free. In fact, it's under Creative Commons. You can also grab it on LeanPub. There, the money goes to EFF, Electronic Frontier Foundation. And I'm also working on a second book. Right now it's 95 pages, and this one is about common C++ coding interview problems, and specifically the implementation patterns that kind of you use to solve these kind of problems. This one, if you want to get it for free, you need to go to LeanPub, but there is a community edition, which is the same as the other one, but you don't have to fill in anything in the form. You can just submit the form empty. That's totally fine. And the benefit is you will not just get a PDF, there's other formats as well. And finally, this is what people might know me for doing, is I run the Daily Bite of C++, which is a series where every day I post a short post about C++, about a specific feature. It's always very short, and it's accompanied with a code example. If you want to follow, I would recommend on LinkedIn, because there I actually do have a reasonable audience, so sometimes the comments are also worthwhile to read. But it's also a Mastodon. I'm on the Hachidem server. If you want to get it by email, then both Medium and Substack have options for that. And they all, both Medium and Substack also support RSS. So if you are still using some sort of RSS reader like me, then go ahead. And if you just want to browse the old archive of posts, I also have that on GitHub, but that I only update roughly once a month, so it tends to be a little bit behind. Okay, so that was 4 minutes of your time, just to promote myself, and now we can start with the talk proper. And the talk is about ranges, specifically what is a range, but I will take a little bit of time to kind of do introduction and talk about the things that were in before C++20, just so we are on the same level. So typically, when we express a range in pre-C++20, we are talking about the range of all the elements in a container. And how you would do that, you would just call begin and end to get the begin and end iterators. Now, a slightly more generic way to do that is to use the begin and end free functions. But if you do that, you need to pull in standard begin and standard end into the local namespace, which gives you the correct fallback if the type doesn't overload begin and end free functions. Now, the benefit of doing it the second way is that it will work not only for types that provide the begin and end methods, it will also work for C-style arrays, and it will also work for types that overload the begin and end free functions. Here it's implemented as a friend, but you can also just implement it in your local namespace as well. And once we have the begin and end iterators, we typically just go over all the elements. So, for example, here we can loop starting from begin, stopping just before end. We get to the next element by incrementing the iterator, and we access the value by the reference. Now, the reason why this works is because conceptually, at least, begin returns an iterator that conceptually points to the first element, and end returns an iterator that conceptually points to one past the last element. Now this is nifty because then we can easily express an empty range where if begin and end point conceptually to the same thing, well, then there are no elements before end, meaning that the range is empty. And we can also easily split ranges into two chunks. If we want to split the range at mid, well, then we can split it into two parts, where we start at begin, stop at mid, and the second chunk naturally starts at mid and stops before end. If you look into documentation, you can also see this described using the half-open interval. For example, on CPP reference, you will see this a lot. This just means that we started first, stop just before last. So just to hammer that properly, if you want to express the range of integers from 0 to 9, you would write that as 0, 10, meaning we start at 0, we stop just before 10. Now, of course, this isn't anything new even in C++. This was all true even in C. So if you have a C-style array, we can get the pointer to the first element. For example, here I'm doing it using array to pointer decay. And then we can get the one past last pointer by simply incrementing by the number of elements in the array. And then again, we can just iterate as usual, starting from the pointer to the first element, stopping just before the pointer that points one past the last, incrementing to get to the next element, and dereferencing to access the value. Now, the reason why we don't really use pointers in C++ that much is because if you try to apply the same logic to a different data structure, well, you need to change your code. So, for example, if we have a linked list, well, here we need to change the way we get the pointer to the first element. We need to change the way we get the pointer one past the last, at least conceptually. And then when we iterate, well, for a linked list that is node-based, to get to the next element, we actually need to read the value of the next pointer that's stored inside of the node. And to access the value, we also need to read the value from inside the node. And really, whenever you have this kind of situation where you are doing conceptually the same thing, like here we are iterating over all the elements, and the code looks roughly similar, that should point you that you are to the fact that you are missing some sort of an abstraction. And iterators are exactly this abstraction, where if we have a linked list in C++, well, we go back to the uniform way of iterating, where we can get the iterator to the first element, the iterator one past the last element, and then we can iterate over all the elements using increment, accessing the value using the reference, and the actual logic of how it is achieved to get to the next element, how we achieve to access the value, that is hidden inside of the implementation of the iterator type. And on top of that, iterators also guarantee that they will only implement operations that are possible in constant time, which then gives us different categories of iterators. So the lowest level is input-output iterators, where we only get the possibility to iterate and access the values. But importantly, both of those operations are allowed to be destructive, meaning that we can only really read the value once. We can only really write to an element once. And once you iterate past an element, that element can be invalidated. This is fixed. This is where the forward iterators come in. They additionally provide the stability of the elements. So now we can read an element multiple times. We can write to an element multiple times. We can iterate past an element, store an iterator to that position, and then come to it back later. This is what the stability means. If you want to iterate in the opposite direction, this gives us bidirectional iterators when you can go from right to left in iteration using the decrement operator. The next level is if you want to jump by integer offsets in either direction or calculate the distance between iterators. This is what the random access iterators gives us. And a new category that is new in C++20 is contiguous iterators. These work exactly the same as random access, with the exception that additionally they also guarantee that the elements are stored in a contiguous block of memory, which means that which is important for performance, because if you have trivially copyable types, You can copy those using memcopy. And if you have those elements then stored in a contiguous block of memory, you can then just copy the entire block using memcopy, and that will be much faster than just iterating over all the elements, copying them one by one. Okay, so that was the intro. Now, finally, what is a range? But we are not in C++20 yet. Sorry for the fake out. So we did actually get a sort of definition of a range, maybe a little bit informal, because we did get the range for loop in C++11. And the range for loop actually does have requirements. It does require that for the range arguments, the expressions begin and end, not specifically like that, but roughly the same meaning has to be true, that the begin and end expressions are valid. It also requires that these return something at least syntactically compatible with an input or output iterator. And then what it will do, it will iterate over the half-open interval that is expressed by the results of the begin and end. And perhaps unsurprisingly, in C++20, we did get the definition of a range that does kind of follow this logic. So here it is captured by a concept that is from the ranges library. And you don't have to understand concepts for this talk, but this concept is simply saying that the type is a range if the expressions ranges begin and ranges end are valid for an instance of that type. Now, this then also gives us a better way to get the begin and end iterators. So this is equivalent to doing the crazy dance with using standard begin and then calling begin, because the complexity of falling back to the default implementation is handled inside of the ranges begin and ranges end. But if you are still working with a container, it's totally fine to just call begin and end methods. There's nothing wrong with that. This is if you're writing generic code and you just want it to work for everything. So again, this will also work for C-style arrays. And because I have been showing you C-style for loops, which you shouldn't be using, you should be using the range for loop. But if you are stuck with iterators, you might not know how to do that. Well, we got another tool that actually gets us from iterators into range. And this is called subrange, where if you have a range that is expressed using two iterators, well, you can then smoosh it into range, and now you can use it as a range in the range for loop. And because ranges begin returns an iterator, and we have different categories of iterators, well, then naturally we also get different categories of ranges, depending on the category of the iterator that is returned. And these are all concepts, so you can in fact use them in your code to constrain arguments of your functions. So for example, here, don't write code like this, and I should say that up front, all the code I'm showing is very explicitly slideware, never use that in production ever. It's just, all of the code is just to demonstrate the point. So this is a very silly function. There is an algorithm for that. I'm just computing the sum of the elements. But what I'm doing, I'm constraining the argument to be at least an input range, because really that is all I need to calculate the sum of the elements. And so this is one way to do it, using constraint auto, but you can also do it using templates. And personally, I like this more because we also get rid of the class or type name keyword, and we use the concept in place of that. So that's a little bit more concise. And also because in the case of a template, we actually named the type. Then if I go back here, I was using deco type to actually go back and access the type again. Well, if you have a template, you have the name of the type directly, and you don't have to use deco type. But one thing I really want you to notice here is that in either case, I'm taking the argument using universal reference. And this is an important point in this presentation. Universal references, because you should always take ranges using universal references. And to kind of demonstrate why, I need to start with another silly example. So this function is broken. It's a very simple function. I give it a string, and it finds the second instance of a character. If it doesn't find that, it returns a reference to local static. Can anyone tell me what's wrong with this? Just shout it out. No, that's fine.
Technically, size team needs to be size team.
That's a good point, but it's slideware. Okay, there's a more fundamental problem with the function.
It accepts array references in the argument, and then it returns a dangling pointer to the character.
Yes, correct. Dangling references. So what happens if I call it like this? So I'm calling the function with a string literal. Like the code itself is totally fine. I have a string literal. The function accepts a string. Totally fine. We can implicitly convert the string literal into a standard string. No issue there. That gives us a temporary standard string instance. We can bind that to a const reference. Also all good. We've, in this case, even find the second instance of the character O. Perfect. We return, we destroy the string, we have a dangling reference. Now, something very interesting happens if I change the signature of the function to take a string view. Is this still broken? Yes, so I have heard the correct answer, which is no, it's not broken anymore. We kind of do the same thing. We call the function with a string literal. We construct a temporary instance of a string view. We bind that temporary instance of a string view to a const reference. Then we find the second instance of the O. We return reference to that. We destroy the string view. Oh, but the important difference is that string view doesn't own its own data. It just points to someplace else. And the someplace else in this case is a global object. It's a string literal. So we have a reference into a global object, and lifetime of a global object will be valid throughout the execution of the program. So perfectly fine. And this difference is something that is captured under the name of a borrowed range. So you might be familiar with the string view that we have I have just shown you. You might also be familiar with standard span. These are types of containers or ranges that don't hold their own data. They simply point to someplace else. And hence they are called borrowed ranges. And if you use range algorithms, they actually do take this into account, where if you call rangeIsFind with a string view, that will work perfectly fine. You will get an iterator back. If you call rangeIsFind with a temporary string, you will get a rangeIsDangling, which is a special type. And this is just an empty type, meaning if you try to do anything with it, you will get a compilation error because it doesn't support any operations. But importantly, if you call rangeIsFind with an L value, meaning that the lifetime of the argument is outside of the function call, well, then the type of the range actually doesn't matter because, again, the lifetime of the argument is outside of the function call. So in either case, this is actually considered that the function is borrowing from outside because we have a reference to something that lives outside of the function call. And this is precisely when the const reference breaks down because we cannot actually distinguish which of these two situations we are in. If we get a temporary string, we are actually taking ownership of the argument, or specifically not just the argument, but the actual data that's behind the argument. And if we get an L value string, well, then we are actually borrowing, and it's totally fine to return references into that, or iterators. And if you switch to a universal reference, well, then you can actually interrogate your argument inside of your function. And as part of that, you can figure out if you are actually borrowing the data, therefore you can return references, you can return iterators, or if you're actually taking ownership of the data, in which case you better not. So if we call it with a temporary string, we are taking ownership. If we call it with a temporary string view, we are technically taking ownership of the string view, but we are not taking ownership of the data because string view itself doesn't have ownership of the data. And if we call it with an L value, doesn't matter if it's mutable, immutable. In either case, we are just borrowing the data. So we can go back and we can rewrite the example to something like this. So now I'm taking any forward range. And if I would change the function to return an iterator instead of reference, I could even downgrade this to an input range. then I require that the range has to be a borrowed range. So either the argument will be an L value, meaning its lifetime is outside of the function call, or if it's a temporary, then the range itself needs to be a borrowed range. And finally, since these are just two categories, like broad categories, and we are operating on something that contains characters, then I also limit that the value type or the element type in the range needs to be a character. And finally, the most important thing, I'm taking the argument using universal reference, and I'm not showing the implementation. It's slightly different, but it's mostly the same. So just to fit it on the slide, I have skipped it. Okay, so I've been talking about taking ranges as universal references and showing you why it's important, but I've also shown you this example at the beginning. Yes?
The question on the previous slide, could you also change your return type? Of the value instead of the reference?
Yes, so you could totally, this is very deliberately crafted to be broken. This is one way to fix it, but yes, like more logically, returning a const reference is weird in this case. Returning value would be totally fine. If I would be returning a mutable reference, that's a different story, because then returning value changes the behavior. You no longer have access to the original element. But yes, you could fix it totally by returning by value.
So you take the universal reference, but given that it's requiring that it be a borrowed range, would it be okay to take an L value reference?
No, so, okay, let me go. It's this problem, because if you have an L value, you cannot distinguish these two situations. So if you take something by L value reference, where the lifetime of the argument is outside of the function call, then that's considered borrowed range. Doesn't matter what is the actual type of the range. Did I have it? Yeah, basically here. So when I'm calling the find with the L values, it doesn't matter if it's a string or a string view, because I'm always taking as an L value reference. Therefore, the function is always borrowing. So if you actually look at the implementation of how the borrowed range concept is defined, it's either the argument is an L value, or if it's an R value, then it looks at the actual type of the range and distinguishes between the situations of a string view, which is itself a borrowed range, versus a string which actually holds its own data. So if you are taking by L value, you are always borrowing. Good enough? Okay.
So does the borrowed range, on the next slide I think it is, so the fact that you're forward range, how does that not activate a move construction? Because if I did that with outbreak using ranges, if it was just, let's say, a standard string L value, it would invoke the move construction, wouldn't it?
So that's the difference between universal reference and R value reference. If you name the type, which we are not doing here, the type is deduced when you call the function. So it's universal reference if the type is deduced for that argument. So this is slightly out of scope. We can maybe talk about that later, but
it's conceptually different to
R value references. Yes, if
it's something that's separately different to look up between an R value reference and the universal reference.
Yes. So basically, if you write the concrete type and you put two ampersands, that's an R value reference. If you have either auto, two ampersands, or you have the argument deduced as part of a function template, then it's universal reference. Those are two very different things. And when it's universal reference, it will either end up as an L value reference or an R value reference, depending on how you actually call it. Right. Yes. So I've shown you this example as well. And you might argue that for this one, it would actually be totally fine to take it by const reference. And you would kind of be correct, because we are just calculating the sum of the elements. We don't really care about the lifetime of the argument. But But there are other reasons, and I have already flashed the slide with the answer, what are the reasons. But the reason why you still need to take ranges as universal references is because we have views. Now, unfortunately, views by themselves is a topic that I could prepare multiple presentations about, and this has already been done by other people. So what I will just do is forward you to this talk, which is fairly comprehensive talk about views. It's on YouTube. I will just concentrate on the things you really need to know about views when you are using ranges. Okay, so what is a view? It's very straightforward. View is a type of range, and specifically it's a type of range that is cheap to move. It has to be cheap to destroy, but that's only required when we have an instance that has been already moved from. And if the view is copyable, it has to be cheap to copy. But it doesn't have to be copyable. And you might think that, well, views, okay, string view makes sense, but that's the completely wrong mental model. And this is the first reason why. Because while string view is always a borrowed range, it's always just pointing someplace else, views don't behave like that. Views will either behave like borrowed ranges or take ownership of the data and not be borrowed ranges, depending on how you actually construct them. So in this case, I'm constructing, where's my pointer? I'm constructing views all, which is the simplest view that there is. It's simply view of all the elements in a range. And if I construct it with an L value, well, then we will end up with a borrowed range. If I construct it with a temporary vector instance, then the view will actually take ownership of the data, and we will end up with something that is not a borrowed range, and the types also change. So in the first case, we get a ref view, and in the second case, we get a type that's called owning view. The types you don't really have to know. That's kind of just like implementation detail. And unfortunately, there is also a second problem why you should be taking, why you should not mix up between string view and views in the ranges library. And it has to do with, really, you should think about views as code. Because views are lazily evaluated, so any logic that's part of the view will be evaluated as you iterate through the elements. So in this example, what I'm doing, I'm composing multiple things. So I have my vector, I take that vector, I wrap it in a transformation. The first transformation will multiply each element by 2, and then I wrap it in another transformation, which will increment each element by 1. So all of this logic, multiplying by 2, incrementing by 1, will be evaluated as you are iterating over the view. And this is on one hand very good, because if you have like a massive vector with millions of elements and you construct a view over that, you only iterate over the first 10 because you have found your special value in the vector already. Well, then you have already run the logic for the first 10 elements, and that's perfect. But you should really keep in mind that this will run every time you iterate over the view. So if you, for whatever reason, need to actually iterate over this view multiple times, you might actually want to manifest the view into a concrete container. One way to do that, this is C++23, range is 2. It will eagerly evaluate the entire view and store it in the specified container. So in this case, we are creating a vector of integers. And then, of course, if you are iterating over the vector, none of the logic that is part of the view will be run because you just have a vector. In this example with transformation, we are still kind of maintaining one aspect of complexity, which is the cost of the view is proportional to the number of elements you have iterated over. But unfortunately, that's also not true, because for some views, the view might actually need to iterate over more elements than the elements you actually want out of it. And the prototypical example of this is the filter view, where in this case, I'm filtering just for even elements. So I start with a vector with just 1 to 5. I filter for even elements. Therefore, the result will be 2 and 4. But importantly, this means that if I get the first element, well, the first element needs to skip over the number 1. So it needs to skip over one element to get to the number 2. And when I go from 2 to 4, again, the filter view needs to skip over the number 3. And this kind of changes the idea of the cost, and in fact this also runs into a problem with the standard library, because if I have an example like this where I don't have any even elements at all, I have only odd elements, well, just to figure out that the view is empty, which we do by comparing begin with end, while I call begin, I need to actually iterate over all the elements. Well, not me, the filter view needs to iterate over all the elements to figure out that there are in fact no even elements at all in the input. And because of that, calling begin now can be a linear operation. And this is something that the standard library doesn't like, because the standard library says that if you call begin, it should be constant amortized time. And so what the designers of the views library decided to do, they decided that, okay, like we cannot really get rid of this behavior because you really need to figure out if there are any even elements. But what they decided to do is to then store the result. So if you call begin again, it will be fast because it's already pre-computed. But for you as users of the ranges, that means that there are many other things to think about. Let me go back. So first of all, because we are caching begin, you better not modify the underlying data structure from that point on. You really shouldn't modify the underlying data structure the moment you bind it to a view anyway. But the moment you call begin, you really shouldn't, because calling begin, mutating a vector can invalidate iterators, and then you end up with a dangling iterator inside of your view. And even if you are using something like a list, which doesn't invalidate iterators on most operations, typically just the affected elements, well, you can still end up in weird situations where we figure out that the view is empty, we push some even elements to the front of the list, and it's still empty because we have already figured out that it is empty. So pushing new elements to the front doesn't really change anything. Now, this is something to keep in mind, but it's not the important part of what you should keep in mind with using views, at least for this presentation. The important part is this. You cannot take it like const reference. Because if you call begin, the view actually needs to store the computed value inside of itself. Meaning if you take it as a const reference, well, it cannot be mutated and you have a problem. This will not compile. So we are back to the idea I was trying to convey. Always take ranges using universal references. Right, so now, because we get, in this case, an R value, because we are passing in a temporary, so we can mutate the R value and everything is fine. So again, when you take ranges, always take them as universal reference. Okay, and since I've talked about views, this is a good point to segue to input ranges, because input ranges can be a bit strange when you use them. And to demonstrate that, I will use a specific type of input range, which is an iStream view. So if you are familiar with the iStream iterator, this is basically a range built around that idea. So in this case, we will be reading from our standard input integers, and on the standard input, we have integers 1, 2, 3, 4, 5, 6, 7, 8, 9. And I will do something very straightforward. I will just have two vectors. I will two times call copy. And what I'm just doing, I take an iStream view, and then I limit the number of elements in the iStream view to 3 elements. So the take will basically limit the maximum number of elements in the view. And you might think that the result would be 1, 2, 3 in the first vector, and therefore 5, 6 in the second vector. But you might also realize that you're at the conference, I'm showing you an example, so that's probably not the case. And if you are in the second camp, you are indeed correct, because we end up with 1, 2, 3 in the first vector and 5, 6, 7 in the second vector. So what the heck happened with the number 4? Well, the reason this happens actually is very similar to the filter view that needs to figure out that it's empty when we call begin. Because how do we figure out that we don't have any more integers on our input? Well, we read an integer. right? So if we are holding an iterator into this input view, input range, well, we have already, by definition, read that specific value. So in this case, we have already read the number 1. And if we are at the end, we are holding the iterator as pointing to number 4, meaning we have already read number 4. Now, and this is where the number 4 disappears. So what actually happens here is we read 1, 2, 3, 4 in the first copy, and we read 5, 6, 7, 8 in the second copy. Fortunately, you haven't lost the number 4 completely, because ranges copy actually returns the ending iterators for both the input range and the output range. But you cannot do it like this, because, and I'm wondering if anyone has a guess.
You can store the stream view and reuse the same for the two.
Not in this specific example, because I'm limiting it to the 3 elements. But yes, you can. You don't get rid of this problem by doing that. But yes, does anyone have a guess why this won't work? It's a concept. Borrowed range. I've heard borrowed range. You win nothing. But you are correct. Yes, because iStreamView is not a borrowed range, meaning that the ranges copy needs to take ownership of the argument and therefore cannot return iterators into it. Well, if we get back our familiar ranges tangling, which we cannot do anything with. But we can fix it, of course. We can just extract it to be an L value and then call the copy on it. And at that point, we will have 1, 2, 3 in our vector, and we will have the number 4 behind the iterator that comes from the ranges copy. And this is not just a behavior for iStreamView. This is something that kind of is prevalent for all input views, input ranges, because the behavior where you need to figure out that you are empty, you already have to have read that specific value is quite common. But depending on the specific input range, the actual behavior might differ. So always look into the documentation of how exactly the specific input range is implemented. Okay, this one will be a short one. This is a category of ranges that's fairly straightforward just from the name. Size ranges are ranges that provide a size. So what you might want to do, so in this case, I'm showing you another view just to kind of, so you have seen a bunch of different views. This is a view iota, meaning that this is just a view that will increment its value as you iterate over it. So it will be just an endless view starting from 1 and then 2, 3, 4, 5, so on. And I limit it to 5 elements, so this will just be 1, 2, 3, 4, 5. Right? And what you might want to do is to just put that into a vector. I have shown you some examples already how to do that. We have used the copy and back inserter. But what you might want to do as well is to actually reserve enough space so you don't end up reallocating the data a bunch of times. But you cannot, because this is not a sized view, because in this case, we actually cannot figure out how many elements we have, even though it kind of looks like that we should be able to do that. In this case, it's not possible because we have an endless range as the first one, and we are just limiting the endless range to 5 elements. But the take 5 doesn't mean specifically 5 elements, it means 0 to 5 elements. And because the take doesn't know that the previous range is endless, well, then it cannot figure out how many elements it has. So in this case, we don't have a sized range, but there is actually a fix for that. So I've already shown you the ranges subrange, and as it has not just an overload for iterators, it also has an overload for ranges, and you can also specify the number of elements. But please be very careful, because this really means that you know what you are doing, because this needs to be correct. If it's not the actual number of elements, it's undefined behavior. So careful with that. But now the wrapped is a sized range. We can then call wrapped size, and it will work again. We can pre-allocate enough capacity in the vector, and all is good.
Excuse me.
Yep.
Go back to the slide. So, could you just have still use iota inside the subrange call? And do you need the counterpart view?
No, because just if you mean just the iota without the take, you couldn't, because then you would have mismatch of elements, because in fact it is an endless view. So
Yeah,
this
I
is
thought if you only evaluate it later, right? Surely, I mean, philosophically speaking, I imagine the subrange could only have to evaluate the first 5.
you are logically correct, but not standard logically correct. So the standard just says like this needs to be the number of elements that's actually in the range, and if it's not, then it's undefined behavior. It's basically it just really serves as an annotation, and it's not meant to be like anything that has additional logic actually checking if it's correct inside of the subrange. Yeah. Well, because the typical overload you use is with the iterators, so that way you can create subranges. But I mean, fair point. If you are doing it like this, it is a bit misleading. That's definitely fair point. But I think the idea is that, like when at the beginning I showed splitting of the range into 2 chunks, then you could take the begin to mid as one subrange and the mid to end as a second subrange. Typically, if you're working like with lower bound, you end up with the middle iterator, and then you can create the 2 subranges that represent the 2 chunks of the range.
So if you do subrange with iterations, the second one doesn't have to be the iterator of the underlying.
Well, it has to be because
So it could be mid.
well, mid is still an iterator into the same range. Sorry, what was your question?
But so that if there's some underlying sequence, like here you're saying that if you're using iota, subrange with 5 on it, the resulting iterator is not going to be pointing to the end of the sequence, like the underlying sequence is unbounded, right? But you say
So iota itself is unbounded.
so you could do subrange with if you got rid of the take, you just had the iota. You could use its begin and advance it 5 times and use that as the.
So you could use, so there are counting algorithms that have underscore n that take the begin iterator and number of elements. And if you have an unbounded range, you could use those algorithms, for example. And I will actually talk about that. What you are asking is going a bit into sentinels. That's the next topic. So perhaps that will be clearer. Okay, and this is precisely this topic. So to kind of finish everything, I will circle back to the beginning and go back to the definition of a range. I did say that a type is a range if the expressions ranges begin and ranges end are valid expressions on that type. Now, that's not the entire story, because both ranges begin and ranges end have additional requirements. Specifically, ranges begin is actually required to return an iterator type. But you might think that the same is true for end, but that's not the case. Ranges end is allowed to return something that is called a sentinel, and the only requirement for sentinel is that it is comparable to the iterator type. So we can just compare the end against our current iterator. That's the only requirement. And this is where we come into common ranges. So if you have, for example, vector is a common range because if you call begin and end, you get the same type back. You get vector iterator in either case. And importantly, if you are using algorithms before C++20, therefore non-range versions of algorithms, they do actually require that both of those iterators are of the same type. Now, if you have something like the iota view, which isn't a common range, well, we then call begin and end. We get different types because end returns, in this case, a sentinel type. We cannot call accumulate anymore, but again, we can fix it. We can add this views common, which turns any range into a common range. So then again, if we call begin and end, we will get back the same type and we can again call the old style algorithms. And you might be thinking, what the heck, what's the point? Because right now it's just more work for everyone. But there are two important points. Okay, I forgot about this slide. If you are using range algorithms, they will also, of course, work on uncommon ranges as well. They just handle it correctly. And this applies not just to the overloads that take the range as an argument, also to the iterator, because they take an iterator and the sentinel for the iterator overloads. The first reason why we have sentinels is, and this is again a very simplified example, is because it can give us easier implementation. So in this case, what I have is a range that counts to 5, from 1 to 5. And in my begin, I return my iterator type, and in my end, I return just the default sentinel, which is a type provided in the standard library. But the important thing that this gives me is that in my iterator, I can just compare against the sentinel, which is essentially comparing to end, because that's what the sentinel means. And I can just express the end condition. So the end condition here is that I have already counted past 5. Right. But there is more important second reason, which has to do with performance. And you can have a situation where you have an input text that is delimited by new lines. And in this case, I in fact verified that we will find a new line at the end. So the validation is actually quite cheap in this case. But then if you want to iterate over the text line by line, so in this case I'm just extracting the first line, we can do it using range is fine, for example, and then we can just wrap it in a subrange to turn it into range. So this is one example how you take two iterators and make them into range again. But this is actually slow. And the reason why this is slow is because range is fine doesn't know that we have the text delimited using new lines. It doesn't know that it is guaranteed that we will find a new line. And essentially what needs to happen, it needs to, in its loop, always check against the end iterator at every step. Because again, it doesn't know that it will eventually find a new line. But if we do know that we will eventually find a new line, we can actually write something like this, where we just look for the new line. That's our only condition. And this will be quite a bit faster because we are doing less comparisons. But it's handwritten code and it's kind of awkward. But there is a special type of sentinel that we can use. We can create an unbounded range where we take our begin iterator and we take something called an unreachable sentinel, which simply compares false, and this is known at compile time, against everything. So the condition that compares the iterator against end inside of the find algorithm will end up at compile time as false, meaning it will completely optimize out. So this will be equivalent performance-wise as our handwritten version where we are just looking for the new line. Right, and the last thing to mention is that if you are writing your own code that doesn't take a range as an argument as a range, which in this case you should be using our universal references, you can also take the range using iterator and sentinel type. And to do that, you can limit the iterator to whatever category of iterator you are interested in. And then you can grab the corresponding constraint for sentinel by just saying sentinel for that type. So this will ensure that whatever is the type is comparable against the iterator. And then you can just use them as you would use two iterators inside of a function. Right, so I have talked a lot about ranges. I've talked about the different categories of ranges that come from the different categories of iterators that are returned by ranges begin. I've talked about borrowed ranges and the implications on lifetimes. When are you taking ownership of the data that's behind the range and when you are actually not. I've talked about views and the important things you need to keep in mind. Views are code that actually runs as you iterate over the view, so it can be potentially expensive. And it can also potentially break the expectation that the cost is proportional to the number of elements, at least in the output. I have talked about input ranges and that you need to be careful when you are working with input ranges. Potentially you can lose some elements if you just naively use algorithms on top of input ranges. I've talked about size range, which simply provides a size method. And finally, we have finished with common ranges. And as I have hammered many times, when you take a range as an argument, always take it using universal reference. Question, yes?
Can you mark your own type as being borrowed?
Yes. It's called enable borrowed range something. But if you search for enable borrowed range, you will find it. And with that, I will thank you for your attention.